Hi, Bobby Phillips here. Today I'm going to go over protein, important for chefs to know about, especially the structure of protein so you can see their impact on cooking. Also, complementary protein. We need protein for tissue growth and repair. Proteins obviously are parts of muscles. They help with transport of nutrients. All enzymes and hormones are proteins, and so on. 4 calories per gram. If a gram is about the size of a paperclip, so if you have 1 gram, a paperclip, of protein, you have 4 calories. There are 20 amino acids, 9 are essential. This means you must consume them in your diet. The other 11 amino acids can be made of those 9 amino acids. So what's important is all 20 amino acids have to be present to build a protein. These are the essential amino acids. No need to memorize them. What would be more helpful is to think of getting a complete protein, which is all the amino acids. Now, again, I'm showing you the chemistry so that you can visualize what's happening. This goes further than your textbook. But what I'm showing you here, as I showed you with carbohydrate and fat, is a carbon molecule. Chemistry often, especially organic chemistry, is based on carbon. What makes proteins unique is that they contain a nitrogen group. This is the nitrogen group. We call it an amino. So what the impact of this is going to be is that when your body uses a protein, it's going to use the amino group. If it doesn't need all of that protein, your body has to excrete that. So the other thing that's significant about proteins is it has the acid group, the carboxylic acid, and that's made of carbon and oxygen and hydrogen. We've seen that before. So again, this is a visual of how protein works. I'll show you in a minute how that impacts cooking. So if you have a amino acid such as valine, it's going to want to connect with the leucine next to it. Again, I wouldn't bother knowing these individual amino acids. What this is simply showing you is that these amino acids want to bond together, the nitrogen group and the carboxylic acid. So amino acids bond together in very specific ways. These shapes, these weird different shapes, represent each of the 20 amino acids. So each, so 20 amino acids have 20 different shapes. That's how we name them. This visual would be a chain of amino acids. If each one of these little dots represented an amino acid, what you would see is a chain of amino acids, just as that previous slide. Now, what these amino acids are going to do is make shapes, and the shape of the protein determines its function. So this is important in cooking because how these shapes form will determine the characteristics of the protein. For example, the protein in gluten, if it's fully developed, it'll be gooey. If meat is overcooked, the shape will be tightly compacted. So all different proteins have all different shapes. Now realize that chain of amino acids is very specific. And what's happening here is an amino acid over here is saying, I want to hang out about an inch from you. This amino acid is saying, I want to be close to you. Kind of like kids in kindergarten who want to sit down for reading time, circle time. And, this guy does not want to sit next to this girl. So there's chemical charges that are going to determine the distance of these amino acids. This is showing the same thing, that chain of different amino acids, realizing to form a protein you need all 20 amino acids. They will connect together in a very specific sequence. Nothing about protein is random. These will be controlled by DNA and RNA. Gives you some hint into bodybuilding and muscle structure. It's very much determined by DNA and RNA. So these amino acids line up in specific structures, and again, these amino acids, the chemical charges determine what the shape is. This shape just looks like a blob of ribbon. It is not at all. This specific sequence has determined that the amino acid here is going to hang out this far from this amino acid, and this amino acid doesn't want to be anywhere near that one, kind of like Charlie doesn't want to sit anywhere near Susie. So this is not random. Here's an example of how not random these structures are. Here is a molecule of hemoglobin, and you see 4 different proteins in very specific structures holding iron so that it can carry oxygen, and that's what red blood cells do. Here's some examples, again, of different types of protein in the body. This shows that glucose uses carbons from protein for energy. This is a messy slide and you don't need to know the chemistry, but realize those carbon molecules, like we have seen before, those 2 carbon fragments, can also come from amino acids. This is the same thing. We saw this before. Those carbohydrates, the glucose can be broken down into 2 carbon fragments. Fat, lots of 2 carbon fragments. And protein, we can get these 2 carbon fragments. Now we can either use these for energy or store them as fat, because these 2 carbon fragments, doesn't matter where they come from, if we get too many of them, we're going to make fat. The difference, as I pointed out, with protein is this nitrogen-containing group. For your body to process this nitrogen, you have to send it to the liver for detox, and then you have to send it to the kidney for filtering. So, problems with too much, you get a strain on your liver and kidney. Also, the mechanisms are not completely understood. You get bone loss. This causes stress on your skeletal structure, of course. It can be harmful to the heart, and most high-protein foods contain a lot of saturated fat and cholesterol. So, obviously, the cost of it as well. I often say to people, if you want to build muscle, you better work out. You better go to the gym and work hard. And to do all that hard work at the gym, you're going to need energy. Energy from carbohydrate, complex carbohydrate. So a bodybuilder will say, well, I eat steak, I eat protein shakes. Well, what's the difference between the cost of a baked potato and a piece of steak? Again, because look at this slide. 2 carbon fragments are 2 carbon fragments. Energy, energy, energy. If you get too much protein, this extra nitrogen causes strain to your liver and kidney. So, too much protein. Very high protein diets can become problematic. Too little protein can result in malnutrition. Marasmus and kwashiorkor are the 2 types. How do we get protein? We eat it. We can also recycle and synthesize amino acids. Remember, 11 of the amino acids are essential, so you must consume them in your diet. That's how your body recycles or synthesizes the 20 amino acids. Now, Digestion and absorption of protein. The first step is denaturation. This you need to know as a chef because denaturation of protein is impacted by heat, acid, bases, salts, and heavy metals. Also, mechanical manipulation. Picture an egg white. An egg white, when it's whipped, mechanical manipulation is denaturing the protein. So that's the first step in digestion. Likewise, you take an egg white, which is solid protein, you expose it to heat, even exposing it to salt will do the first step in digestion, which is denaturation. So you can see this with salt. You can also see this with lemon in something like ceviche. The second part is enzymatic digestion. This occurs in the small intestine. In the stomach, protein is cooked just like the slide I showed you, denaturation. Realize denaturation, the acid here can come from the stomach. So the second process, it begins in the stomach. It continues with enzymes in the small intestine and the pancreas. So this is breaking down enzymes into the individual amino acids that your body may need. So protein quality in the diet. We need all essential amino acids. With the essential amino acids, we have a complete protein. This means we have all 20 amino acids. So that is obviously in foods of animal origin. Can we get protein from non-animal origin foods? Absolutely, but we need to be a little bit more thoughtful in how we choose those. So, for our purposes at this point, know that all 9 essential and then the other 11, so 20 amino acids are present in foods of animal origin. I'll continue this on the next screencast.